We have reached the last piece of the puzzle before we can start building our first machine learning algorithm. So far, we have learned, at least conceptually, how to input data into a model and measure how close to the targets are the outputs we obtain through the objective function. However, the actual optimization process happens when the optimization algorithm varies the model's parameters until the loss function has been minimized. In the context of the linear model, this implies varying W and B. Okay? The simplest and the most fundamental optimization algorithm is the gradient descent. I would like to remind you that the gradient is the multivariate generalization of the derivative concept. Let's first consider a non-machine learning example to understand the logic behind the gradient descent. Here's a function f of x equal to 5 times x squared plus 3 times x minus 4. Our goal is to find the minimum of this function using the gradient descent methodology. The first step is to find the first derivative of the function. In our case, it is 10 times x plus 3. The second step would be to choose any arbitrary number. For example, x naught equals 4. X naught is the proper way to say x0. Then we calculate a different number, x1, following the update rule. xi plus 1 equals xi minus eta times the first derivative of the function at xi. x1 is equal to 4 minus eta times 10 times 4 plus 3, or 4 minus eta times 43. So what is eta? This is the learning rate. It is the rate at which the machine learning algorithm forgets old beliefs for new ones. We choose the learning rate for each case. By the end of this lecture, the concept of eta will be clearer. Using the update rule, we can find x2, x3, and so on. After conducting the update operation long enough, the values will eventually stop updating. That is the point at which we know we have reached the minimum of the function. This is because the first derivative of the function is 0 when we have reached the minimum. So, the update rule. xi plus 1 equals xi minus eta times the first derivative at xi will become xi plus 1 equals xi minus 0, or xi plus 1 equals xi. Therefore, the update rule will no longer update. Let's illustrate this with an example. Let's take an eta of 0.01. We start descending. x1 is equal to 3.57. x2 is equal to 3.18, and so on. Around the 85th observation, we see our sequence doesn't change anymore. It has converged to minus 0.3. Once the minimum is reached, all subsequent values are equal to it, since our update rule has become xi plus 1 equals xi minus 0. Graphically, the gradient descent looks like this. We start from any arbitrary point and descend to the minimum. Alright, the speed of minimization depends on the eta. Let's try with an eta of 0.1. We have converged to the minimum of minus 0.3 after the first iteration. Now, knowing the minimum is minus 0.3, let's see an eta of 0.001. This step is so small that we need approximately 900 iterations before we reach the desired value. We descend to the same extremum but in a much slower manner. Finally, I'll try with an eta of 0.2. We obtain a sequence of 4 and minus 4.6 until infinity. No matter how many iterations we execute, our sequence will never reach minus 0.3. We already know minus 0.3 is the desired value, but if we didn't, we would be deceived. This situation is called oscillation. We bounce around the minimum value, but we never reach it. We can use 4 or minus 4.6 in the algorithm, but this won't be its true minimum. Graphically, we are stuck into these 2 points, never reaching the minimum. Now that we have seen different learning rates and their performance, let's state this rule. Generally, we want the learning rate to be high enough so we can reach the closest minimum after repeating the operation in a rational amount of time. So, perhaps 0.001 was too small for this function. At the same time, we want eta to be low enough so we are sure we reach the minimum and don't oscillate around it, like in the case where we chose an eta of 0.2. In the sections in which we will study deep learning, we will discuss a few smarter techniques that would allow us to choose the right rate. Alright, there are several key takeaways from this lesson. First, using gradient descent, we can find the minimum value of a function through a trial and error method. That's just how computers think. Second, there is an update rule that allows us to cherry pick the trials so we can reach the minimum faster. Each consequent trial is better than the previous one with a nice update rule. Third, we must think about the learning rate, which has to be high enough so we don't iterate forever and low enough so we don't oscillate forever. Finally, once we have converged, we should stop updating, or as we will see in the coding example, we should break the loop. One way to know we have converged is when the difference between the term at place I plus 1 and place I is 0.001. Once again, that's a topic we'll see in more detail later. Please download and look at the Excel file associated with the gradient descent, available in the course resources section. We encourage you to play around with the learning rate or the arbitrarily chosen number x0 and see what happens. This will give you a good intuition about the learning rate, which is central to teaching the algorithm. In the next lesson, we will generalize this concept to the n-parameter gradient descent. Thanks for watching.